So today we are starting chapter 15, chemical equilibrium. So chapter 14, which we just finished, was kinetics, and now we're going into equilibrium. So first of all, what is equilibrium? Last chapter we were all talking about the rates of the reaction, how fast the reaction was moving forward. But we can also have a reaction that moves both ways. We can have a reaction that moves forward and backwards. This is called a reversible reaction. And the way that we show this is with reaction arrows that go both ways. For example, here we have dinitrogen tetroxide. Reaction arrows go both ways with 2 moles of nitrogen dioxide. The reaction goes both ways, which means that you can have the forward reaction and the reverse reaction. Both are going to have their own rate. When those rates are equal, meaning the rate that is going forward is the same speed as the rate that is going backwards, then you are at what is called dynamic equilibrium. Dynamic equilibrium. What does the word dynamic mean? Something is dynamic. What is it doing? Changing. Good. So the rates are the same. Your relative concentration of reactants and products are going to be constant, but there is still a change going on here. What's happening is the reactions are still going on. This reaction is still running forward. That's still happening. But the reaction in reverse is happening at the same rate. So your relative amounts of your reactant and products are staying about the same, but you are still having these reactions going on. This is not static. Static means nothing's moving, everything is just frozen. This is not a static equilibrium. This is a dynamic equilibrium. So they are still moving, they're still reacting. It's just because the forward reaction and reverse reaction are happening at the same rates, your overall concentration of everything is going to remain constant. So if we look at the concentration of reactants versus products for that reaction at time 0 over here, we have all reactant, no product. As time goes on, we start losing our reactant and start forming our product here. At some point, they're going to level off. At this point, you have reached equilibrium. So equilibrium is reached when these amounts, these concentrations, no longer change. So somewhere around here probably is where you've reached equilibrium. You no longer see your concentrations changing. This is where the forward reaction at time 0, the forward reaction has some sort of initial rate. The reverse reaction at time 0 has a rate of 0 because you don't have any products yet, so the reverse reaction can't start going. But as time goes on, eventually your forward reaction starts slowing down. We saw that last time. As you get less reactants, the concentration reactant goes down. Your reaction slows down because they're less concentrated, less likely to bump into each other. But then we start having this reverse reaction starts happening. I'm starting to get products, so the reverse reaction can start happening. On this graph, this point right here, 2 rates become the same. That is where you have reached equilibrium, when the rate of the forward reaction and the rate of the reverse reaction are the same. So you can tell where your equilibrium has been reached by either, if you're looking at the concentrations, where the concentrations stop changing, or if you're looking at the rates, where the rates become the same. So those are the 2 graphical ways of identifying where equilibrium has been reached. So, as I said, this is a dynamic equilibrium. These reactions are still taking place. And the rates of the reaction forward and reverse are equal. You can only establish equilibrium with reactants, with products, or you can establish it if you start with a mixture of reactants and products. Now, the example we just showed at time 0, you had no products. But you can get to equilibrium if you started with products, in which case the beginning of the reaction is the reverse reaction that's running faster. Or you can start with a mixture of both reactants and products and still reach equilibrium. So in this chapter, we're going to be learning about if you have some sort of reaction and I tell you, well, here's your initial concentration of reactants and or products, if you have a mixture of both reactants and products, figure out where equilibrium occurs and what those concentrations are at equilibrium. So that's the math in this chapter, figuring out what the concentrations of all these things are when you have reached equilibrium. So, equilibrium constants. In the last chapter, we had rate law constants. What was our symbol for a rate law constant? K. Now, when we first learned about it in chapter 4, learned about rate law constants, I made this big deal out of make sure that when you write K's for your rate law constant, it was what, uppercase or lowercase? Lowercase. And why is that important? Because now we're going to have an uppercase K that means something different. So, while the lowercase k is your rate law constant, now we're going to have an uppercase K that is your equilibrium constant. Your equilibrium constant. So again, we said at equilibrium, your rate of your forward reaction is equal to your rate of your reverse reaction. So looking back at that reaction we had in the first section, our K, F stands for forward. This is your forward reaction. So your forward reaction, the rate is equal to the equilibrium constant times the concentration of your reactant. The reverse reaction, now your product is considered your reactant, and you have K of that reverse reaction. So these two things are equal to each other when you are at equilibrium. So if you set these things equal to each other, put your K's on both sides here, you end up with the ratio of your rate law constant for the forward reaction over the ratio or over the rate law constant for the reverse reaction, and we are going to rename that a new constant, uppercase K. That's your equilibrium constant. This little C stands for concentration, because this is in terms of concentrations. Remember, that's what the brackets means, concentrations. So what we ended up here was that this equilibrium constant was equal to NO2. Was that our reactant or our product from the original? Was NO2 our reactant or our product in the first equation? That was a product. So this is going to be equal to the concentration of our products over the concentration of the reactants. Here. Now, why do you think there's a little 2 right there? There's a square. Where do you think that came from? Good, the coefficient from the stoichiometry there. That's where it came from. It's the coefficient from your equation. So we're going to call that, we'll just call that N and M for whatever your coefficients are. So unlike in the rate laws where you had to experimentally determine what those orders are in the equilibrium expression here, it's just going to be the coefficients from your balanced equation. You don't have to experimentally determine what those powers are. If you have more than one product, then you'll just keep on going. Product 1 raised to its coefficient, product 2 raised to its coefficient, etc. And this is going to be called your equilibrium expression. Your coefficients from the balanced equation. So I think I've got somewhere here. Let me go back. There. So here is our equation again. N2O4 is at equilibrium. That's what these arrows mean, equilibrium arrows, with 2 moles of NO2. So that's where the 2 came from. The 2 came here is your coefficient from the balanced equation. And then N2O4 just hadn't understood 1, so that's why its power is just 1. So if I wanted to calculate Kc, uppercase Kc, your equilibrium constant here, I would just need to know what are my concentrations of my relative reactant and product at equilibrium. So that would be done experimentally. Go back a slide real quick. So here's a table of initial versus your equilibrium concentrations of these reactants and products. And there's 5 different experiments here. And what we find here is that regardless of what our starting concentrations are, so in this first experiment we started with all reactant, no product. In the second experiment we started with mixtures of both. In the last experiment here we started with no product or no reactant and all products, so that reaction is going to start running in reverse. Regardless of how much concentration we started with of the 2 reactants and products, look at the equilibrium concentrations here. When we take the ratio of our equilibrium concentrations, there's our equilibrium constant, it's pretty much the same. About 4.6 something times 10 to the negative third. So the equilibrium constant, it does not depend, it's calculated by your initial concentrations, but it does not depend on those initial calculations or that initial concentrations. It's calculated by your equilibrium concentrations, which, assuming that you are doing this experiment under the same pressure and temperature, is going to be the same ratio here. So we got the same K value, this is your Kc, regardless of what our starting concentrations were. All that matters is that ratio of your equilibrium concentrations. Reaction quotient, Q. So reaction quotient. Reaction quotient is calculated the exact same way as the equilibrium constant. It's still concentration of products over concentration of reactants. The difference is it does not necessarily have to be at equilibrium. It can be at any point during the reaction. It can be the beginning of the reaction. It can be at equilibrium, in which case at equilibrium QC and KC are equal to each other. Or it could be if you overshot equilibrium and you start going backwards to get back to equilibrium. It could be at any point in the reaction. But the equation is still going to be the same. It's going to be the concentration of the products over the concentration of the reactants. So for a sample equation, A plus B goes to C plus D. Here are your products. So that's what goes on the top, your products. And here are your reactants. That's what goes on the bottom, your reactants, raised to whatever their stoichiometric coefficients are. So if you're following along the textbook at this point, we are on page 668, and this is equation 15.1. The equation for reaction quotient. It's only our first one. Oh, okay. First one for this chapter. It is quantitative chemistry. Technically, chemistry 1 is considered qualitative chemistry, which obviously there was math in it, but just not nearly as much as we're going to have this semester. Great news, right? All right, let's see if we can calculate something with this. All right, so carbonyl chloride, which is COCl2, also called phosgene, is a highly poisonous gas that was used in the battlefield in World War I, phosgene gas. Very bad stuff. It is produced by the reaction of carbon monoxide with chlorine gas, both of which are also deadly gases. If you carbon monoxide poisoning, and then of course chlorine gas, you don't want to drink or you don't want to breathe that either. In an experiment conducted at 74 degrees Celsius, the equilibrium concentrations of all the species involved in this reactions were as follows. Now, these are all in gas states, but we can still calculate their concentrations here. So the concentration of carbon monoxide, concentration of chlorine, and the concentration of the phosgene. So the questions here, number 1, write the equilibrium expression, and number 2, determine what is the value of that equilibrium constant for this reaction at 74 degrees Celsius. Now, temperature was nowhere in our equation for the rate law or the equilibrium constant here. The reason why they're specifying the temperature is, as we will see in a later section, changing the temperature will change your equilibrium constant. So they're just putting that 74 degrees there as a disclaimer saying we're not changing the temperature here. So let's open a new slide here. So first of all, here is our equation. Now, it's already balanced for us. It's nice and 1-to-1. So first of all, the equilibrium expression, Kc, is equal to, what's going to go on the top of our equilibrium expression? Good, COCl2, and we're going to put in brackets because this is the concentration of. Is this going to have any power? No, it's going to have an understood 1. What's going to go on the bottom of it? Good, CO and Cl2. Now both of those are also going to be an understood power of 1 because they both had coefficients of 1. And you're done. You just wrote the rate law. There's part A. Or sorry, the equilibrium expression. Why did I write B? Can you tell it's also 8 o'clock in the morning for me? All right, so part B asks you to use the provided equilibrium concentrations to actually calculate this equilibrium constant, Kc. So that means we're going to take those values from the last page. So COCl2 was 0.14 molar. CO was 1.2 times 10 to the negative 2. And then chlorine was 0.054 molar. Molar. What do we get here? Good, 216. Now, even though if you look at this, the units don't really cancel out for the equilibrium constants, they're considered unitless. So we're not going to put any units on this. We're just going to say 216. Well, actually, we've only got two significant figures here, so it's not 216. It's actually what? 220. Good. Or to show that that 0 isn't significant, we'll put it in scientific notation, 2.2 times 10 squared. And there's our answer. Why is it not a good idea to leave it as 220? Why did I put in scientific notation there?
Some people count the 0 and some don't.
Yes, because if I leave it as 220, it's ambiguous whether or not that 0 is significant or not. So by writing it in scientific notation, I showed the 0 was not a significant figure. It is. All right, so how bad was that one? Not bad. We can do that. 12 of those on the test and we're good, right? All right. So we oftentimes will just calculate the reaction quotient. Again, the reaction quotient is the exact same formula. What's the difference? It has a Q instead of a K. That's a big difference, yeah, because we're looking for a reaction quotient instead of an equilibrium constant.
Oh, it's not at equilibrium.
It may not be at equilibrium. It could be at equilibrium, in which case Q and K are equal, but it does not have to be at equilibrium. So the caveat for K is it has to be at equilibrium. Here, we can calculate Q for at any point in the reaction. So we're just told at any point in the reaction, I went in and I measured those concentrations of reactants and products here. Here, if I calculated Q at time 0 here, at time 0, for this one, we've got the reverse reaction, here, versus at any particular time, we get different values of Q. By the time we reach over here, which it looks like from the picture, at that point, looks like we've reached equilibrium. It looks like they're bottoming it out here, plateauing. This is probably going to also be our K. But the Q varies at different points in the experiment. By the time you reach equilibrium, at that point, Q and K will be the same. So let's try this out. Write the reaction quotients for each of the following reactions. I'm not asking you to calculate anything, just write what is the reaction quotient. Let's do the first one. And then I bet you guys can do the after that. So what goes in the top of the reaction quotient for part A? NH3, does it have a power? What's its power going to be? Good. What goes to the bottom? And good. How bad was that? Can you do the rest of these? Go ahead and do those. All right. Everybody feel good about all of your reaction quotients here? Any of them seem questionable? Move on. All right. So what does K tell us? Back in chapter 14, when we were calculating little k, the reaction, the rate law constant, it told us about the speed of the reaction. So the bigger that your reaction, your rate law constant was, the what your reaction? Faster or slower? If you had a really big K, what did that tell you about the speed of the reaction? Very fast, good. Whereas if you had a really small K, that was a really slow reaction. So we can also learn things from the magnitude of uppercase K, our equilibrium constant. So there are three possibilities when you are reaching equilibrium as far as what our concentrations of reactants and products look like. And these are all on page 671. The first possibility is the reaction will essentially go to completion and your reaction mixture will be mostly products. So reactions mostly products, you have very little reactants at the end of the reaction. The second possibility is the reaction won't occur forward very much at all. And at the end of the day, when you hit equilibrium, you're still mostly reactant with very little product. And then the third possibility is that you go forward, not about halfway, but to a certain degree, but not all the way, to the point where at the equilibrium you have comparable, not exactly equal, but comparable, at least the same order of magnitude, amounts of both reactants and products. So those are the three possibilities for your concentrations at equilibrium. And it depends just on the reaction and the conditions under which the reaction occurs. Some reactions that we may need for industrial processes are falling mostly into that second category there, where they don't occur forward very much, but we need them to occur forward, so we need to change the reaction conditions in order to force the reaction to go forward more. All right. So when the magnitude of K is very large, so a very, very large number, then you can expect that first outcome. You're mostly products. We know this from fractions. If your products go on the top of the fraction, that's your numerator. Very big numerators equals a very big number. So when you have a very big K, that meant that your numerator was very big, your products were very big, you had mostly products. So that's when you have a very large K. So I'd say that's more than like 100, a K value more than 100, then you're mostly products. So for example, here we have silver ions in solution reacting with ammonia aqueous to make aqueous silver ammonia. Here the Kc is 1.5 times 10 to the 7. That's a very big Kc. So that means at equilibrium you are mostly on the product side of that reaction. Very little unreacted reactants left over. Now, the opposite, when the magnitude of K is very small, I'd say smaller than 100th, or 10 to the negative 2 or smaller, then you expect the second outcome, which is that the reaction, when it hits equilibrium, is still mostly reactant. There's very little products. So very, very small products, your numerator is small, but lots of reactants, your denominator is big, will make the fraction become a very small number. And again, I'd say that's below 100 or below 10 to the negative 2. So for example, here is nitrogen gas reacting with oxygen gas to make nitrogen monoxide. Now, looking at this reaction, why for us as humans on planet Earth would it be a bad idea for this reaction to readily occur very easily at 25 degrees Celsius or room temperature? It would take up all the oxygen in the air, right? Because our air is mostly what? Nitrogen. So if the nitrogen in the air can consume the oxygen through this reaction that makes nitrogen monoxide, which we can't, we can't breathe that, it doesn't help us, then this would be very bad news for us. All the nitrogen in the air would gobble up all the oxygen and we'd all be in trouble. Luckily, the Kc for that is very small, 10 to the negative 25th, which means that at equilibrium, it's still mostly reactants. Good news for us because we kind of need this reactant right here to live. Now, if your equilibrium constant is an intermediate value, so they define an intermediate value as somewhere between 10 to the second and 10 to the negative second, or somewhere between 100 and 100th, then you're that third possibility where you have comparable amounts of reactants and products when you are at equilibrium. Any questions about the equilibrium constant or the reaction quotient? How to write those expressions? Yes?
So the Kc, like you can determine if it's equilibrium, if it's times the 10 second, that.
So if in this case, either you would calculate Kc or I would tell you Kc and ask you at equilibrium, is this reaction mostly reactants, mostly products, or comparable amounts of both? Yeah, but I would either give you Kc and you would say what category does it fall into here, or you would calculate it. But if you were calculating it, that's because I gave you the concentrations of everything, which is, at that point, you can probably tell from the concentrations which ones are bigger. So the one that we did where we calculated and we found that it was 220 was our Kc. I'd say, because that's a power of 1 to the second, I'd say that that would be that third possibility. At equilibrium, your comparable mixture of reactants and products. All right. To me, this chapter is a little bit shorter and a little bit easier than chapter 14, as long as the math doesn't scare you too bad. All right, so next we're talking about heterogeneous equilibrium. What does heterogeneous mean? Different. Yep. So back in chapter 1, way back, we had heterogeneous mixtures versus homogeneous mixtures. So homogeneous mixtures were the same throughout. Heterogeneous mixtures were different compositions throughout. So a heterogeneous equilibrium is going to be when you have some sort of a reaction that they are not all in the same state of matter. So for example, here we have carbon dioxide reacting with solid carbon to make carbon monoxide. This is a heterogeneous reaction because if you look at it, carbon dioxide and carbon monoxide are both gases, but carbon here is a solid. It's a different state of matter. Well, why is that important when you're writing equilibrium expressions? The problem is, can you have concentration, brackets, means concentration of, can you have concentration of a solid? No, you can't have concentration of a solid. So for this reason, we could technically call it just like 1. The concentration of anything that is a solid is just going to cancel out. So when you are writing out these equilibrium expressions, you are going to ignore any pure solids or pure liquids. So
pure liquid when it has like the liquid above the L, or
yep, it has the L. Aqueous is fine. Aqueous still has a concentration, but you can't have a concentration of a liquid. You can have a concentration of a solution or a gas, but you cannot have concentration of a liquid or a solid. Solids. Yep, you exclude them. You just leave them off the equilibrium expression. And by that same rule, you exclude them from the equilibrium expression or the reaction quotient expression, since they're both calculated the same way. So the tricky one here, usually that most students have trouble with, is water, H2O. Water, in different reactions, can usually be either a liquid or a gas. Gases can have concentrations. You can have the concentration of water vapor in this room right now. That is a concentration. That is fine. So if H2O is in gas form, it will still appear in the equilibrium expression. But if it is in liquid form, you will leave it out of the equilibrium expression. So that's the tricky one. Most students are fine with the other things, like clearly carbon solid, it shouldn't have a concentration. But H2O is the tricky one, because we see that oftentimes as both a gas or as a liquid. If it's a gas, it has a concentration, it's in the equilibrium expression. If it's a liquid, then we ignore it. And obviously if it's a solid, we ignore it, but we usually don't have reactions that occur with solid ice. All right, so let's write some more equilibrium expressions, but now these are heterogeneous equilibrium expressions. So the first one we have up here, calcium carbonate goes to calcium oxide and carbon dioxide. Uppercase K. So again, products over reactants. Now in the case of A, here's our products. Do we get to put both products or just one? Just one, just the carbon dioxide, because calcium oxide is a solid, raised to 1. Now, do we have anything in the denominator here? No, why not? Good, our reactant is a solid, so we can ignore that. So there's our reaction equilibrium expression for that first reaction. That's all that's there.
So would there ever be anything that, like if there was two solids in the reactants and like a gas in the products?
In which case you just have a 1 on front. Yeah, you just put a 1 on top if both of the products are left out. And we're going to see that when we get to D here. Yeah. Actually, let's just go ahead and skip ahead to D. So D here the numerator is the products. H2O right there is a liquid. So we're going to ignore it. There is no other product. So we're just going to put a plain old 1 in the numerator there. So for D, what would we put in the denominator? Good, the O2, and then the H2. What special thing did we do to H2? Square. Good, because it has a coefficient of 2, so that gets squared. Manipulating equilibrium expressions. So if I change something about the reaction, how is that going to change K? This is very similar to what we did back in Chapter 5 with Hess's law. We all loved Hess's law, right? Yeah. So in Hess's law, we were manipulating thermodynamic equations, and as we changed the equation, it would change the value of our enthalpy term. You doubled the reaction, you doubled your enthalpy. You reversed the reaction, it reversed the sign of your enthalpy term. Same thing here, we're going to manipulate the equation, and then that is going to change our value of K in some way. So looking at this first equation here, Kc of this reaction up here, concentration of products over concentration of reactants. Now, what is the relationship between this first equation and this second equation? What did I change? How did I manipulate that first equation to get the second equation? Swap reactants and products. So I reversed the equation. Reverse the equation. If I rewrite the equilibrium expression, because I reversed the equation, that swapped the numerator and the denominator, right? Numerator and the denominator swapped. What do we call that when we swap a numerator and denominator, taking the what of it? Reciprocal. So because we took the reciprocal of our equilibrium expression, we're going to take the reciprocal of our equilibrium constant. So if you reverse an equation, your new equilibrium constant is the reciprocal, or 1 over, your original equilibrium constant. And these rules are going to be summarized in a table for you. If you're following along in your book, we're on page 674. If I told you what K was for a reaction, and then I said, well, what would K be of the reverse reaction? Then you would swap it. Or you would take the reciprocal of it. All right, so first possibility, we can take the equation and we can reverse it. Second possibility, comparing, again, equation 1 to equation 2, what have we changed from equation 1 to equation 2? We doubled it. Good. So we multiplied by a factor of 2. Now, once again, I'm going to see how is that going to change our equilibrium expression. So that's going to change just the powers of the concentration units here. The order is going to be the same because the order of the reaction is the same. All that's going to happen is I'm going to go from having a 2 on the NO to now a 4 on the NO2 here. When I did that strange line there. 10. When I did that here, basically everything went up to twice its original power. So twice of a power is the same thing as squaring it. So if you multiply the equation by 2, you're going to take your K value and you're going to square it, not multiply it by 2. You're going to square it. So what do you think would happen if I tripled my equation? Cube it. Good. So whatever the factor is you multiply your equation by, that's the power that you're going to raise your K value to. This next one to me is basically the same rule there. No. Thought that was the next one. What if I, instead of doubling this, what if I halved it? If I halved the equation, what would happen to my K value? Take it to the 1/2. What do we call something to this 1/2 power? It's what? Square root. Good. So I'm going to jump ahead and show you the table. There it is. There. So this is the same table on page 674. So the first one, if you reverse an equation, your new K is the reciprocal of the original K. If you multiply your equation by a number, then your K value is raised to the power of that number. If you divide by a number, then your K value is raised to 1 over that power. And then the very last one is if you take two equations and you add them together. If you take two equations and you add them together, you would take their K values and multiply those together. So in Hess's law, we were dealing with enthalpy and manipulating these things together. When we added two equations, we added their enthalpy values. Here, when you add two equations, you're going to multiply their K values.
How come we have to do it in the, the expression, and why not when you get the final answer, you do all those things?
You could do it once you have the final answer. I could just give you the K value and ask you what's the new K value. It's just showing you in the expression how this came to be. Why. Yeah, basically, once you identify that it's reversing, you can take your K value and take 1 over it. Or once you identify that you're adding two equations together, you can just multiply their K values. Assuming you were just given the K values, which for these problems, I am just going to give you the K values. Hopefully it'll make more sense once we do an example.
I get it, I just didn't know if I was thinking about it.
All right, so let's try an example. I think this will make more sense. The following reactions have the indicated equilibrium constant values at 100 degrees Celsius. So I have equation 1 and equation 2. Determine the value of K for the following reactions at that same temperature. So let's look at equation A here. So equation A. Which equation, 1 or 2, did equation A come from? 1. How was equation 1 altered to make equation A? Reverse. So this is the reverse of 1. reverse, I'm just going to leave that there because it's annoying, of number 1. So if it's the reverse of number 1, how are we going to find its k value? One over, good. If the equation is reversed, your k value is 1 over your original k. So it's going to be 1 over the original k, which was 0.014. So what is 1 over 0.014? Yep. We'll just round that to 71 because we've got 2 sig figs. So 71 is your new k value. What about equation B there? Equation B also came from the first equation, but how do we manipulate it? Multiply by 2, good. So this is number 1, equation number 1, and we multiplied it by 2, which means its k value is going to be what? Squared, good. So that should be a small number. .0 times 10 to the negative 4th. Little number. Equation C, how did that one come to be? Half of equation 1. So number 1 times a half, which means its k value is going to be what? Good. The square root. So what's the square root of 0.014? .0.12, good. How do those first 3 feel? Do that? All right, D there. D, we've got something else going on here. Yeah. Yes. All right. So let's say we take these 2 equations and we add them together. Is anything going to cancel when we add them together? Yeah, what cancels? Bromine. Br2 will cancel when we add them together. So we end up with 2 NOBr. Yeah, I'm just going to leave it there because it's just annoying me now. You know, really, it hurt me. I took that as a challenge. 2 NOBr gas phase. Whew. Plus the Cl2 gas phase. And on this side, we have the 2 NO and the 2 BrCl. What did I just write? BrCl. Gas phase. All right, so that is equation D. So equation D was number 1 plus number 2. So what is my k value? Are we going to add their k values? Times them together, good. So it is the product of the 2 k's. So our k value is going to be 0.014, the k for the first one, times the k for the second one, which is 7.2. Yep, 0.10. Yeah, let's look at the last one. The last one, I'm looking at that, that's clearly got both equations in it. But what happened to get to that equation? Because it's not just adding them together. Something else had to have happened there. They were reversed and halved. Okay, so they were added together, they were reversed, and they were halved. Ooh, that's a lot going on there. So at this point, because we've already calculated D of them added together, if we wanted to, we could just take that k value, reverse it, which means 1 over, reciprocal of it, and then square root it. or we could start at the beginning and go back to the original K values. Either way is fine, but since we've already got the K value for this equation forward, we're just going to say take D, and we're going to reverse it and divide by 2. Save us a little work. Reverse and divide it by 2, or 1/2. So we're going to take that K value, and if we reverse it, what does that do to the K value? Turns it, and then we're going to do what? Square root. So what's the square root of 10?
3.16.
Good. So 1 over 0.10, and then to the 1/2, or square root 3.2. So to me, that's even easier than Hess's law.
Yeah, it's not that bad.
Yeah, because DE there is like the worst we could possibly do. We added them together, we reverse them, we have them. I mean, there's like no other complicated thing you could do there. And just keep track of how K changes with each one of those manipulations. All right. So we said earlier that you can't have your equilibrium expression in terms of a liquid or a solid, but you can have it in terms of a gas or an aqueous solution. So we're familiar with aqueous solutions having concentrations, but gases, we very rarely talk about gases in terms of their molarity. Back in chapter 10, we were learning about gases when we had mixtures. We were talking about them in terms of their partial pressures. Dalton's law, the total pressure is equal to the sum of the partial pressures. We generally keep track of how much gas we have by its pressure, rather than trying to calculate its molarity like it's easy with a solution, aqueous solution, to calculate its molarity. With gases, it's much trickier. We're usually talking about it in terms of its pressure. So for a reaction that everything is going to be in the gas state, or at least everything that's going to go into the equilibrium expression is a gas state, we can rewrite this equilibrium expression in terms of the partial pressures instead of in terms of the concentrations. So remember those brackets here that we're seeing? Brackets means concentration of in units of molarity. We're going to take those away and replace them with a P, which means the pressure, sub whatever that species is, so the partial pressure. And we're going to take Kc and turn it into Kp. What does C stand for in Kc? Concentration. So what do you think this P stands for in Kp? Pressure. So in other words, you can calculate the equilibrium constant in terms of its concentration, or if it's a gas, in terms of its pressure. But you can only do this if the only things that go into the equilibrium expression are gases. If you have a mixture of gases and aqueous things, then you can't do this. This is only if everything is a gas, or at least everything that goes into the equilibrium expression is a gas. You can have solids and liquids because we're going to ignore them anyways. But only everything that goes into the equilibrium expression is going to be a gas. So let's get back to the equation here. All right. So here's our equation to convert between Kc and Kp. So this is equation 15.4 on page 677. And it says that Kp is equal to your Kc times RT, R being gas law constant, T being temperature. By the way, what unit does that temperature have to be in? Kelvin. Why do we know that T has to be in Kelvin? Good, because R is always in Kelvin. Raised to delta N, where delta N is how many moles of gas were in your products minus how many moles of gas you had in your reactants. Yes, so this is a power. Raised to the delta N. Now, notice just the RT is raised to that delta N. The Kc is on the outside of that parentheses. So when you are doing this, make sure you keep track of where your parentheses are in your calculator. Only RT is raised to that delta N power. And then on the outside of that, you multiply by Kc. So here, in order to write the rate expression in terms of Kp, we write it the exact same way that we did in Kc. But instead of putting things in brackets, meaning concentration of, we're going to put them in parentheses and put them as the subscript of P, meaning that is the partial pressure of each of the species in the reaction.
But we're going to do the same thing that we did before. If there's a coefficient in the equation, it becomes the power of that reactant or product. And if you have anything that is in the liquid phase or the solid phase, they are going to be left out of the equilibrium expression. But otherwise, as you can see here, Kp equilibrium expressions are written in the same way that Kc equilibrium expressions were written. If you are given Kc, you can calculate what Kp is using the equation that we saw earlier, where you find delta N is equal to the number of moles of your gaseous products minus your number of moles of gaseous reactants. So in this particular reaction, we have 2 moles of nitrogen dioxide on the product side, and we have 1 mole of dinitrogen tetroxide on the reactant side, and both of those are gases. So delta N, your change in N, then is going to be equal to the 2 moles of gaseous products minus that 1 mole of gaseous reactants, so delta N is equal to 1. Then you plug everything into the equation. Kc was given in this problem to be 4.63 times 10 to the negative third. R, we're going to use the value of R in terms of atmospheres, so 0.08206 liter atmospheres over Kelvin moles. T, you need that temperature to be in Kelvin in order for it to cancel out with the units in our R value. And in this case, our N, delta N is 1, so that second term RT is just raised to a power of 1. And we get what our Kp value is here. So next we're going to compare what Q versus K can tell us to see whether or not a reaction is going to proceed forward, backwards, or whether or not you're already at equilibrium. So we already said earlier the reaction quotient Q, which is calculated in the same way that K is, the same expression, just you don't have to be at equilibrium. But if you are at equilibrium, it's the same as K. Now, if you calculate your reaction quotient and you end up with a number that is smaller than your given K, then that means that the denominator, which are your reactants, are too big. So the denominator of the fraction is too big, that will make Q too small. In that case, your reactants are too big and you need them to get smaller. They'll go smaller by reacting forward. So in this case, if Q is smaller than K, the reaction will proceed in the forward direction. And this just means that your equilibrium has not yet been reached. So you have to go forward to reach the equilibrium. If Q ends up being larger than K, then that means in your reaction quotient, the numerator was too big. And the numerator, again, is where you find the products. So if the products are too big, then to make them smaller, you're going to have the reaction run in reverse. So when Q is larger than K, the reaction is going to run backwards or back to the left in order to reach equilibrium. Now, when we are talking about Q and K here, we can be talking about Q or K in terms of the concentration or in terms of the pressure. These rules still apply. So if I'm giving you a reaction, I'm asking you what's going to happen to these concentrations, and I haven't told you whether or not the reaction is running forward or backwards. If you have amount of both reactants and products, you always have to double check and see, okay, is this reaction going to go forward or backwards? So let's look at an example here. At the start of this reaction here, you're given amounts of both reactants and products. So we have nitrogen plus hydrogen makes ammonia. And I've got amounts of both my reactants and my product. I've got amounts of ammonia here at the start of the reaction, which means, first of all, we don't know if this reaction is running forward or backwards, or it could already be at equilibrium for all we know. So in order to answer this question, which is asking, is it at equilibrium, and if not, which direction it has to go, forward or backwards, in order to get there, we have to calculate what Q is and then compare that Q to K. So let's go ahead and write our equilibrium expression for this reaction, or our reaction quotient expression. So Q is equal to the concentration of products over the concentration of reactants. So our products are ammonia raised to the second power because there are 2 of them in the reaction. And on the bottom are our reactants, so that's our nitrogen and our hydrogen. And hydrogen will be raised to the third power because there are 3 of them in our reaction. So we go ahead and plug in the values that they gave us for those concentrations of each of these. Don't forget when you plug these in your calculator to keep track of which ones get squared or cubed, which ones are in the numerator versus the denominator, so be very careful about where your parentheses start and end. Because you don't want to end parentheses too soon and have things get kicked out of the denominator and up into the numerator, and you also don't want to not have enough parentheses and end up having things cubed that should not have been cubed here. So if you plug all of these into your calculator, you should get 0.61. So QC is equal to 0.61. Now let's compare QC to the KC that they gave us. They gave us a KC value of 1.2. So QC is smaller than KC. So if QC is smaller than KC, that means the equilibrium hasn't been reached yet. You still have too many reactants, and therefore the reaction is going to have to proceed in the forward direction or to the right in order to reach equilibrium. So we've talked about how to determine K from the concentrations, but we haven't yet talked about how to do the reverse. Given K, determine what those concentrations are. So let's look at this simple reaction between the isomers of cis-stilbene and trans-stilbene. If we were to write the expression, we'd have trans over cis, because trans is our product and cis is our reactant. We're given that this has a Kc value of 24.0, which means at equilibrium we have relative concentrations of both the trans and the cis value of stilbene. If we set up what's called an ICE table here. ICE table is an acronym. I stands for initial concentration, C stands for change, and E stands for the equilibrium concentration. And in this case, we were told that we were starting with an initial concentration of our reactant cis-stilbene of 0.850 and then no trans-stilbene. So we know automatically this reaction is going to proceed forward because we don't have any product to proceed backwards. If you were given a problem that had both concentrations of reactants and products, you would first have to calculate Q, just like we did in the last example, compare it to K to see if you're going to have reactions going forward or backwards. The reason why that's important is this center here, change. Here I have the change written as negative X for our reactant and positive X for our product. This is because we know the reaction is going forward, so our reactant's going down and our product's going up. If the reaction was running in reverse, you would switch these and your reactant would be going up plus X and your product would be going down minus X if you calculated Q and found that it was greater than K. So we would write our rate expression Kc is equal to our product over our reactant, so trans over cis. Then we plug in those equilibrium concentrations. Now here, instead of just having the concentration, we have these concentrations in terms of X. In this case, X is the concentration of trans, that's our product, so that goes in the numerator, and 0.850 minus X is our concentration of the reactant, so that goes in the denominator. Now these are 1-to-1, so in that case we have everything raised to the first power, but don't forget, if you do have a coefficient of 2, then that would be squared, etc. At this point, we set this equal to the Kc value that was given to be 0.24 and solve for X. When we solve for X, in this case, we get an X value of 0.816, and we do this just using algebra, so move the denominator over the other side, distribute the 24, solve for X, etc. Once we have that X value, we can plug that back into our ICE table for the equilibrium and determine what our equilibrium concentration is. So for example, our equilibrium concentration of trans is X, therefore it is 0.816. But our equilibrium concentration of the cis is 0.850 minus 0.816 molar. And therefore we can determine what those equilibrium concentrations are from the K value. Now this is a very simple, straightforward solving for X. Next time we'll see, well, what happens when the algebra gets a little bit trickier for more complicated equations.